Hello friends, today we are discussing about the power supply, which is the content of our BSc elective PHE 10, that is Electrical and Electronic Circuits course. And we have been discussing about power supplies quite often because they come across our daily life, as you must have seen in your laptop chargers or your mobile chargers. So you can always have a DC voltage which is required for our general purpose operations of many devices or the gadgets that we use daily. Along with that, certain instruments that you operate in your laboratory are requiring the DC voltages of particular value which are required for smooth operation of our instruments. So for that we have circuits which are called power supply, which are able to give DC voltages of our required value, which may be fixed values like say 5 volt, 10 volt, 15 volt, plus minus 10 volt, 12 volt, so on and so forth as per the requirement. Or sometimes even we have variable supplies, like I may have a voltage which is ranging from 0 volt to 10 volts, or I may have a supply with 0 to 30 volt range. Means I am going to have a DC voltage of my requirement from the circuit, that is the power supply. In this picture, if you see on the right hand side, I am showing you particularly the instruments which you encounter in our laboratory, which are called these power supplies, which are able to give us the required regulated voltage as well as current. But all these instruments basically are working on the AC voltage or the AC mains voltage that comes to our house through the electrical supply company's input. As you know, that is in India we have a 230 volts 50 hertz supply as the input supply for our households. Now how do we get that converted into the DC voltage of our required value is what we are discussing in today's topic. If you look at any power supply module, then it will be consisting of following steps. First, you have to convert that mains voltage into a lower voltage using certain device called transformer and a step down transformer if you want a lower voltage. Then you convert that AC voltage from the transformer output into DC using a circuit called rectifier, and for that we can use diode circuits which can give us full wave or half wave rectification as the need may be. And then the output of that rectifier, though it has certain DC component in it, is not fully ripple free or pure DC, but it is always ridden with certain kind of AC component in it, which is called a ripple. Now to get rid of that ripple, we have to use another circuit block, and that is called filter. That filter will be removing the AC component from our rectified output, and then that output of filter, which is completely rid of all the AC component, can be used to generate or derive a DC voltage of our requirement through a regulator circuit of constant voltage. A block diagram of a typical power supply is shown here, where the AC supply is stepped down using a transformer, then a pulsating DC is generated by a rectifier. The DC component only is required, which is given by a filter circuit which removes all the AC components from our circuit and gives us a DC. But this DC is not a regulated DC. That DC will be depending on what is the input voltage is. Like if there is variation in our input voltage, then naturally, as you know, the input of the main supply, say for example instead of 230 volts, it shoots up to say 260 volts, or it comes down to say 200 volts, then that same thing, that is variation at the input, is going to be reflected proportionally at the output of our step down transformer, which is going to get rectified, but not going to get corrected. So that same variable output of pulsating DC will be handled by the rectifier, and the filter will also remove that AC component, but still will be giving us a DC voltage which is proportional to the input voltage, and if it has got certain variations in input voltage, those same variations will be proportionally reflected in the DC voltage generated by the filter. So we call that DC voltage, that is output of a filter, as unregulated DC. And by using a circuit called voltage regulator, we convert that unregulated DC into a fixed DC voltage of our requirement, which is the requirement of our load. The load is the instrument that we are going to connect to our power supply in order to functionalize it. After removing the AC component from the rectified output using a filter, we need the circuit which is going to give us constant DC output voltage. And this is done by a circuit called voltage regulator. There are different types of voltage regulators. One is the linear regulator, which is operating throughout the cycle of all through the AC, and so there is no ripple problem, but its efficiency is less, as we will be seeing when we see the operations of these regulators. And there is another kind of regulator which is called a switching regulator, where we are using a device to charge and discharge and supply a DC voltage to the load. But in this particular case, since we are going to switch on and off charging of that particular device, we are going to have a ripple which will be riding on the DC that we are going to get at the output of the switching regulator. We are not going to discuss this switching regulator today, though it is power efficient, but it is noisy. So we will restrict our discussion to the linear regulators, which are less efficient, but they don't have any ripple in them. Now in both the regulators types, the input is derived from the rectifier filter circuit, that is, we are using unregulated DC. The principle of linear regulator is simple, that you are going a rectified and filtered input V in, and you are giving it to the linear regulator circuit, and output we are getting a regulated output which is smaller than the input that we have got here from the unregulated input. What we are doing here is that we make the input unregulated voltage to pass through the regulator circuit, and it compares it with a fixed reference voltage, and that fixed reference voltage will determine what output is to be sent to the regulated output. And the excess of the voltage, that is the difference between the output and the input, that excess voltage is actually dissipated within this circuit as a ohmic loss or in form of heat. So it is not a very efficient circuit because we are losing on a power here, but we are getting excellently good results about the regulation in this case. Now these linear regulators are also having two types within them, a shunt voltage regulator and a series voltage regulator or a series pass regulator. The shunt voltage regulator, we have the load which is connected in parallel with the reference voltage. The reference voltage is derived through particular device, as we will be discussing, and we put our load directly parallel to that particular reference voltage. So we are always going to have a fixed voltage which will be equal to the reference voltage, but it is not a very efficient circuit, as will be discussed soon. In series voltage regulator or series pass regulator, we connect the load in series with the variable element that drops the excess voltage between the input and output across it. Okay, that is called the series pass element, which actually does the dissipation part of it. But these kind of circuits are very commonly used. Most probably you will come across always the series voltage regulators only, because they are efficient on the power side. Now we need the reference voltage device which will be giving us a rock steady reference voltage irrespective of any conditions like change in the input voltage, change in the current flowing through the device, or change in, even for that matter, ambient conditions like temperature, humidity, so on and so forth. And one of the best candidate that is used for generating a reference voltage is a Zener diode. As you know, a Zener diode is a device which is again a PN junction diode only, but the doping is very high, and so the depletion region between the P and N junctions is very thin. So when we apply a forward bias to this diode, it just operates like our normal rectifier diode. It will be having this forward bias characteristics, which is exactly same as our normal any other diode. But in case of the reverse bias, what happens is that when we give certain voltage across that depletion layer. Due to the thinness of that depletion layer, it allows a lot of charge generation in form of avalanche or in form of Zener breakdown, and we get a current which gets sustained in that particular device and which pins the voltage across the device to a voltage called breakdown voltage or a Zener voltage. Now, in this particular case, this breakdown is not a permanent deformity, or it is not going to destroy the device. Whenever you reduce that particular reverse voltage across it, it will again come back to its normal operation. So, operation of Zener in breakdown region is not going to destroy it as it would have done for any other rectifier diode. But this breakdown voltage Vz is going to be fixed for a particular given device, and it is characteristic of that particular Zener diode that you choose to use in your circuit. Once you choose that particular Zener voltage, then come what may, whatever current you pass through it in under reverse bias condition, you see here I am changing the reverse bias current here. However, the voltage across this device is remaining rock steady at Vz. So now I have got a solid state device here which is going to drop a voltage across it which is steady irrespective of the current flowing through it or irrespective of whatever the other conditions that it is subjected to. So this makes a very good source or a instrument for us to derive reference voltage for our regulator circuits. And so now if we use this Zener into a shunt voltage regulator, I have shown it here. What we have done is that we took a Zener diode and we connected it to a positive terminal to its cathode. That is, we are operating it in the reverse bias mode with a resistance between the supply and the Zener. And since we are operating this Zener in a reverse bias condition, the voltage across it is going to remain constant as we discussed earlier, the Zener voltage, the reference voltage, across which we are putting the load. So this load is always going to see the same voltage which is the Zener voltage. So now here we are successful in having a constant voltage delivered to the load, and this is what was our requirement for a regulator, that it should deliver to our load a constant voltage irrespective of what other things happen. So this is the way it is operating. Now what is happening here? Since this Zener is going to draw Vz as the voltage across it, and if say Vin is the rectified input that we are getting, then the balance of Vin minus Vz is going to be dropped across this resistance. So this is going to be our dissipative element in our shunt voltage regulator. Now there is a condition for the Zener to get operationalized, is that there is a minimum Zener current that you have to always allow to pass through it, and that is the IZ minimum. That is the rating given to you by the manufacturer of the Zener diode when you buy one. So you should ensure when you design a circuit that your Zener will always keep on getting at least IZ, and your load is going to get IL, which is nothing but Vz upon RL, the resistance value of this load. So this IL is essentially going to be now different depending on my load value. Okay, my Vz is going to be fixed, but my IL may change depending on my RL. Now what we have to consider here is that the input current that we are supplying is getting divided here in two parts. One is going to the Zener, other one is going to the load. The voltage across the load remains constant irrespective of the load resistance at its value. So IL will be determined by the value of load. But now you remember one thing, that if I have got say smaller load value, then I need higher IL to flow it. Now in order to keep the minimum IZ flowing through Zener irrespective of whatever is IL, my IN, the input current, has to be enough to cater for Zener current minimum, at least IZ minimum, plus maximum load current IL, and that much of current is going to be always flowing through this R, that is I am going to always dissipate I in square into R as the power across this. And whether my load is high or low, I will have to always keep on bleeding this current. If I draw lesser IL, this higher current will flow through IZ. But effectively, I in has to be high all the time. As you see it is not a very efficient way of working, but still it is providing us for quite normal purposes a steady voltage that we require for our operations. If I just take a small example here, if we want to design a shunt voltage regulator using a Zener, then say consider that we need to deliver this regulator a 5 volt DC for a load which is varying between the range of 100 ohm to 500 ohm. My RL is changing from 100 ohm to 500 ohm, anywhere it may be, and my input voltage is 6 volt. So in order that I need 5 volts across my load, my voltage rating of my Zener should be 5 volts. So I should have a VZ of 5 volt. Now I have to calculate my load current. When I am having the load of say 500 ohms, then 10 milliampere current will flow through my load. 5 volt upon 500 ohm is 10 amps. But if my load resistance reduces to 100 ohm, then 50 milliampere current is going to flow through my load. I have to cater for the maximum current that I require. So if IZ minimum, the minimum current required for the Zener to function as a voltage reference is say 5 milliampere, then I need here the input current drawn from my rectified output is 55 milliampere, because 50 is the maximum load current that I require and 5 is the current I require, 5 milliampere I require for my Zener operation. So total of 55 milliampere. When load resistance is minimum, only 5 milliampere will flow through the Zener. But if the load is maximum value, then the current through Zener will be the entire 55 milliampere minus 10 milliampere which will be flowing through the load. That is, my Zener will be having to pass through it 45 milliampere. So my power rating of my Zener has to be in a way catering for the maximum Zener current that may be passing through it, that is 45 milliampere into the Zener voltage 5 volt, so which comes out to be 0.225 watt or approximately quarter watt. So quarter watt rating 5 volt Zener will be the requirement. And now remember, if my input voltage is 6 volt, then that resistance R is going to drop across it 6 volt minus my VZ 5 volt, that is 1 volt, but current through it is going to be 55 milliampere always, so its value will be 18 ohms. And as you see, this 18 ohm resistance is always going to drop across it 55 milliampere current, so it is a very dissipative kind of configuration that we are using, though whether I require in my load just a 10 milliampere current or 50 milliampere current, irrespective of that, always I am going to drop 55 milliampere current into this 18 ohm. So it is a highly inefficient way of operating. So this is what we considered about the load regulation, is the changes or the correction that we get when load is changing. But now we can always have, say, even in the rectified input that we are getting is unregulated. So say it varies between V in 1 to V in 2. It is any value. As I said that you may get any value because of the change in the input supply itself. Then what happens here is that whenever the input may change, this VZ is going to remain constant. Okay. So the voltage drop across resistor VR is now V in minus VZ. This VR is going to vary as per the availability of the input voltage. The load current that is going to pass through this load is also constant as far as the load is constant. Okay, so this IL that is going to pass through this load will be fixed, which will be equal to VZ upon RL. So if RL is not changing, then this IL is constant. The drop across this R is going to be determining the input current that is going to flow through this, and it will determine by this V in, whether it is V in 1 or V in 2. Depending on that, this resistance voltage will be V in 1 minus VZ or V in 2 minus VZ. So my I in will be depending on this resistor voltages. So this I in is going to change, but IL is going to remain constant. So all that extra variation in the current that is going to happen here is going to be borne by this Zener. The Zener current is going to be sometimes going in excess because the voltage at input has increased, whereas Vz is still rock steady at Vz. Okay, so power dissipation that is going to happen in the Zener device is going to be now quite high, because I am going to have increased Iz with respect to or as dependent on the input variation. So the rating of the Zener has to be calculated not just on the basis of load variation, but also based on the expected changes in the input supply also. So this is how our design will be refined when we do it with the shunt regulator. But we can always have a better version, and that is called the series pass voltage regulator. Here we have a variable element placed in series with the load here. Okay, the reference voltage is given to this series element, and which is going to control the current which is passing through this in order to give enough or appropriate load current. By changing the resistance in this series pass element, we are going to change the drop across it. So here is our V in, here is our V out. The excess voltage that is dropped is by this series pass element will be determined by the current that is passing through it. Now since we want these two variable and which should be controllable electronically depending on our reference voltage, we need to have an active device as our series pass element. The first choice, easiest choice, is a transistor, because we can always control the voltage across this transistor VCE depending on the current that is flowing through it as well as the base current that we are supplying it. So we are using here emitter follower configuration of an NPN transistor as the series pass element, and here we are giving the reference voltage to the base of this transistor. Now since this transistor is going to be conducting in its active region, this VBE, the base emitter voltage of this transistor, will be constant of the order of say 0.6 volts if it is a silicon transistor, and so the voltage that appears at output of this series regulator is nothing but the voltage Vz minus VBE that is dropped across it. So the voltage at this output is lesser than the reference voltage by VBE or 0.6 volt. Now in this case our load current is nothing but the emitter current that is flowing through this transistor. Voltage drop across this transistor, the collector emitter voltage VCE is nothing but V in minus V out. Okay. Now the current that is going to be given to the base of this transistor is going to be determined by what kind of load current we need, because this load current is nothing but the emitter current. So if we know IE, we know that beta, the current gain of this transistor, will require a very less base current to be provided by our reference circuit. So we are not going to be loading our reference circuit also, so our reference also remains very much stable because we are not loading it. And the current that is going to flow through this resistor also is now going to be just the minimum current that I require for my Zener to operate, Iz mean, plus the base current that I require for this transistor to operate. So it is much lesser than in our earlier requirement of very high current all the while dissipating through this R. So it is the efficient circuit than the shunt regulator, because requirement of load current is less as far as the base current is concerned, and so there are less losses in this resistor. And advantage is there is that because of the series pass element regulator, we can also have a possibility of feedback configuration. Now what is happening is that earlier we were always saying that the reference voltage is there, it is fixed, and that is just going to be determining factor at the output. But if by any chance we are going to have sudden changes in our output conditions, then that may not be catered for easily with the reference voltage itself. But if we can have certain feedback where we are sampling the output voltage which is coming across the load and feeding it back to a kind of a comparator which compares this signal of the sampled voltage to the reference voltage and generates an error signal to control the series element. Then we are having a better efficient way of operating our circuit, where we are essentially taking the consideration the changes in the load condition or component behavior also into consideration and making the corrections. Typically, comparator, as you know, operational amplifier are the best circuits that you can think of as a comparator, because they have a extremely high gain, and so with two inputs you can generate output which is a very highly correcting. The circuits discussed so far, let us reflect on that, and then we can just compare it with our feedback circuit, how it is going to be beneficial. The circuit that we discussed so far, we are providing the output voltage only equal to the reference voltage, and the values of reference voltage were generated through the Zener, which comes normally on nominal available values, like 3.3 volt is there, or 3.9 volt, or 4.3, 5.1. These are typical values of Zener voltages that you get. So always your reference voltage will be only at that value, and once a particular Zener is placed in that circuit, the output of that circuit is fixed to the corresponding value, say like either it will be Vz or Vz minus VBE. The output voltage is fixed and will never be larger than the reference voltage. But this feedback component can allow us to even have higher voltages than the Zener voltage rating as our output voltage, and this is what I have shown you here. In this particular case, we are using this sampling circuit in form of a potential divider. R1 and R2 are the resistances, and this voltage across R2 is fed back to the comparator as the error signal or the feedback signal, which is given as a negative input so that you get a correction. The V feedback is R2 upon R1 plus R2 of VO, but V feedback is equal to V reference, so V output is R1 plus R2 upon R2 into Vref. So now here we are able to generate output voltage which is even larger than the reference voltage. And why only higher voltage? Instead of the fixed R1 and R2, if I apply a potentiometer which is a variable resistance, then the variable terminal of the potentiometer, if I connect to the feedback circuit, then I can always vary this and change the ratio of R1 and R2, and so I can always change my VO by changing the proportion of R1 and R2. So here we are able to even generate a voltage which is variable voltage by this variation in R1 and R2. So we are successful not only in getting the voltage which is higher than the reference voltage, but also a variable voltage than the reference voltage. So I thank you here for your attention, and I hope that you have today got some glimpse of how a DC voltage regulator is designed and how it is useful in our day-to-day life. Thank you very much.